Thanks, Dave. Yeah, maybe we should go to the pub, hey? Anyway, I'd thank the organisers of the conference. It's been very interesting. Thanks for allowing me to talk. As I say, I'm going to be talking about some open source code that we have for solving tsunamis and flooding. Just give you an overview of that and maybe a few comments about our experiences with open source. And this is a project with Geoscience Australia, so the idea of open source with government departments, which I think has worked out very nicely for us between the ANU and Geosciences. So we actually got some exposure, I think it was back in 2009 now, a few years ago already, where we actually got up on the New Inventors. It was one of these shows, not actually an invention, it was a special, and I guess the Victorian bushfires had just happened over the summer, and then Queensland had some floods, and so they had a show on basically disasters, hazards and what have you, and invited us to talk about flooding. And they made a little package, 1 minute package, which actually sort of covers essentially what I'm going to talk about, so maybe you can go to the pub after I've given you the package. But that was sort of an interesting experience in itself. I think we spent a whole day just trying to get this, and I must admit it was a little bit harrowing. I was a little bit nervous, to be honest. I should push something on here to plug in.
2004 Indian Ocean tsunami caused terrible destruction and killed almost 300,000 people.
Let me stop that now. Let's talk about, is it lighting?
We have developed a tool to help plan evacuations and to do
It's called ANUGA. ANUGA is a computer program that can simulate how water flows. It can, for example, model the impact from tsunami inundation, the consequences of dam breaks, riverine flooding, and flows around structures. Water can be a very complex material. Even your kitchen sink sees complex water flow phenomena, just like this hydraulic jump in the water. ANUGA can model these complex hydraulic jumps, using them to build a whole body of water as a collection of triangular cells. The software then computes the hydraulic jumps between each of the adjacent cells. The result is an accurate and robust simulation of the whole event. The power of water is terrifying, no matter how it arrives at your door. ANUGA is a solid foundation on which to predict complex water events far into the future.
I think they cut me there.
Looks familiar.
Anyway, so as I say, that's a quick overview of what we're on about. So ANUGA comes from ANU and Geoscience Australia, GA. So I think that was done over a beer or something. So probably not the best name in the world, but it rolls off our tongue. I'll talk about what we use it for and what its capabilities are. I'll talk a little bit about tsunamis. This actually is a cut-down version of basically a public lecture on tsunamis. So that I'll cut a little bit of that out, and then talk about some of the validation that we do and why we're using open source. So what is it? It's an open source, free and open source software package. What can it do? It can model the impact of basically flooding of one sort or another, so dam breaks, flooding, storm surge, tsunamis. Its history was actually as a dam break simulation software with ACTU. So ACTU is the local ACT, Electricity and Water Corporation, and we wanted to do some hazard maps around water supply reservoirs, these reservoirs that are up on the top of hills, but in urban areas. So we wanted to run some more sophisticated simulations than had been done in the past. And then from that, we got involved with Geoscience Australia, and we were developing a storm surge model back in 2004, and got quite a way into that. But then the tsunami, Boxing Day tsunami, happened at the end of 2004, and of course the view of the politicians obviously came focused very much on tsunami modelling, and so we changed it from a storm surge model to a tsunami model. And that actually was quite timely for us because we were able to get perhaps a little bit more support than we might have expected. And as I say, it's developed between ANU, the mathematics department, myself and other people in the department, students and other researchers, and the people at Geoscience Australia, and in particular in their risk assessment group. So, and I guess the idea from the GA point of view was that they wanted to get a better feeling for what was under the hood of these hydraulic models, and hence build up some expertise themselves in that side of the project. And they've gone on and extended the software and applied it to a number of case studies around the coast of Australia, and actually internationally. They've got projects through AusAid with Indonesia and the Philippines in particular at the moment. So what do we use it for? Well, as I say, tsunami modelling. This is actually a case study in Wollongong, and it so happened that Emergency Management Australia was just about to have an emergency practice of their emergency response just after the Boxing Day tsunami, and so I think they were going to have some other sort of hazard happen, but they rushed and asked for a tsunami inundation instead. So we showed what would happen at Port Kembla, and got picked up by the local RAG, of course, by the Illawarra. Can't remember what it's called. Mercury, yeah, Illawarra Mercury. So we got a splash on the front page of Wollongong to be flooded, sort of thing. But actually, we ended up working and continue to work with the people in the council in Wollongong. So they've actually got involved in the development of the software. So they're civil engineers for the most part, not programmers. But they've been able to add quite a lot of functionality to the software. And I guess that's where the open source comes in, and it's written in Python for the most part. So that's where the ease of learning the language comes in. So tsunami modelling, I guess that's GA interest, at least initially. Riverine flooding, that's actually been sort of the extension that these people, people in local councils have gone. They want to know more about, if someone's going to do some sort of development, what will happen to the floods. Also, when you're doing developments, you have to put up bridges and embankments and what have you, and that changes the flow markedly and may flood areas that weren't being flooded before. So they want to be able to do simulations like that. So that once again is sort of related to our interaction with the councils, local councils, and the sort of classic dam break, which actually was in a sense the first application that we had for this software way back. In the late 1990s, actually, now. And that was written in MATLAB at the time. So, what can it do? Well, what is it? You can solve, there's a very precise model of fluid flow called Navier-Stokes equations. If you average them in depth, you get shallow water wave equations. And so, if your water flow is seen to be very shallow relative to the extent in which you're interested in, then the shallow water wave equation is generally a pretty good model for that. And because they're two-dimensional instead of three-dimensional, they're much easier to solve, or at least you can solve over much longer times. So for instance, a tsunami is basically whatever the depth of the ocean is, which I guess might be, 10 kilometres. And of course, the distances you're looking at is 1,000 kilometres. So you're looking at sort of like a thin, thinness of a piece of paper over relative to the size of a piece of paper. So that's thin. So tsunami problems are definitely shallow water type problems. Basically flow over the surface for the most part is shallow because you're interested in quite large distances relative to the depth of water that you're working with. But in these situations, you do get interesting complex structures in your flow. So in the piece with New Inventors, we had the water in a basin, and you're getting these hydraulic jumps. So you get the water coming down, going out at supercritical speed, and then the basin sort of stops it, so that slows it down, and that's much higher sort of depth of water. And then you get this very distinct region that goes from the deeper water down to the shallow water, or from the supercritical flow to the subcritical. They're hard to deal with because the equations we're working with are sort of differential equations, and you've got this jump, so they're not differentiable. So you have to work with that, and actually the methods we use explicitly look at those places where you have the jumps and solve a conservation law to actually solve what's going across those hydraulic jumps. So our whole model is based around dealing with hydraulic jumps, and hence it can deal with hydraulic jumps. So about 10 years ago, that actually was a very unusual characteristic of a piece of software. Most of the software was based on finite difference approximations, and essentially they couldn't deal with hydraulic jumps. They couldn't deal with this transition from sub to supercritical. So we actually got a jump on a lot of the other codes. Indeed, it's only recently in the last few years that even some of the commercial codes that are very popular here in Australia, for instance, have caught up and have developed these sort of finite volume based type methods. But that gives us a chance to sort of jump, do another leapfrog, and then hopefully they'll catch up again, which I'm sure they will. What does it do? Also, it deals with the wetting and drying, which is another problem. Once again, there's sort of a degeneracy in the equations going from wet areas to dry areas, and so you have to almost explicitly deal with that change of behaviour. Anyway, so our code does that reasonably well. From my point of view, I'm in the mathematics department. I'm interested in developing algorithms for interesting problems. So all these things are still research interests and still more to be done. So I have PhD students working on a couple of these points still, and I expect that they'll be working, maybe not those particular PhD students, but there will be PhD students working on this sort of stuff, I think, right through my career. Okay, so here's our hydraulic jump for the kitchen sink. That's a hydraulic jump. We have water coming down a channel, for instance, and hitting some sort of barrier. So that's obviously simulation. That's a simulation as well. There's sort of hydraulic jumps. When you have a tsunami rolling in, it starts off as a fairly sort of broad wave, but as it gets closer inland, the higher part of the wave goes faster than the lower part of the wave, and hence you actually build up into a sort of a shock coming onto shore. And you probably would have seen something like that in those dramatic videos from the Japanese tsunami recently. So you sort of see that it's a very distinct sort of wave coming in. So what's it being used for with GA? GA has been using it to test or to quantify, I guess, the hazards around Australia. So you've obviously got the problem of where the tsunami is initiated. So places like Indonesia will initiate tsunamis. New Zealand is a bit of a problem for us on the east coast. So anywhere along the west coast of New Zealand, either north or south, and along the coast and to the ocean above, to the north and to the south, places where a tsunami can be initiated. From south, it's beautifully lined up. Sort of New Zealand goes down there, and then the Alpine Fault goes further down, and then that bit is beautifully lined up with Hobart. So sort of like a lighthouse, just generate this tsunami along a fault, and then the tsunami propagates perpendicular to that. as I say, Hobart's probably the most obvious place to get hit by something from New Zealand. Anyway, so the idea is to go around the coast, work out the most at-risk areas, and then have some idea of how high the waves would be, etc., and hence be able to provide fairly quick response to there's an earthquake of a certain magnitude out at the south of New Zealand, then that should imply something happening somewhere else. And of course there are these measurement buoys, these dart buoys that are in the ocean, and they measure the pressure of the water, which means they measure the depth of the water. And so they can measure a wave, a tsunami wave going over those, and they can integrate that information with a set of pre-computed solutions to come up with a reasonable estimate of the effect of any specific earthquake or tsunami. So these are just different places we've worked with where it might be being used. You can do quite reasonable things here. It's not too obvious, this picture, unfortunately, but there's a picture of a flood in Wollongong again, and you can see this little sort of hydraulic jump that's been formed there. Unfortunately, you can't see it, but this elevation data actually does have things like the median strip here on the road, and once again you can't quite see it, but it actually also does have the gutter as well. And unfortunately, you can't see it, but there is actually a hydraulic jump sitting, at least I can't see it from this angle, sitting there. So you can actually get down to that sort of level of detail. The elevation data comes from LiDAR data, so these are these laser-based imagery. So most councils would have data of this sort of resolution. So in theory, they could do this. But they don't have the software necessarily because it's too expensive. Hard to convince a manager to fork out, $30,000 per year on something like this. And secondly, quite often they don't have, they haven't been trained to run this stuff. So often they'll get consultants in, and they'll produce something like this. Often the consultants will keep the data, which is silly, and they, in a sense, can't run it again, and they can't fiddle with it. So there is an advantage in having access to the software.
How long does that take to produce?
That sort of refinement, well, that's a good question in the sense that we're always trying to get the code to run faster. I would say that might actually take a couple of days to run at that sort of refinement. But we're, as more and more cores become available, as more and more GPUs become available, there's great hope that instead of days or even weeks for these sorts of things, will be down to hours or even minutes in some of these things. So that's a project that we're definitely going down. Like I say, this is actually written in a combination of Python and C, so probably more Python than it should be, to be honest. So there's even an opportunity to speed this up probably by a factor of 5 by putting a little bit more stuff into C or C++.
How much do you use the graphics cards for processing?
At the moment, none at all. We've got a project where we're looking at porting it across, but there are other packages that are actually quite similar to ANUGA in their framework, and hard to know. You hear all these reports. It's a speed up of 500 times, these sorts of things, but what that actually means, we're still working on. But in theory, you could probably get away with single precision sort of output for this, so that'll double it up or have a factor of 3 or 4 on that. So there's great opportunities to basically, have a $2,000 box and say, here's your ANUGA box sort of thing. What do the council people like to do? Well, they get a development application that says, hey, why don't we build a new, a Bunnings or something, perhaps, here, and it's absolutely going to do nothing to the flooding. And of course, usually that means, the council can't really do much about that because they haven't got the resources to test that. But if you've got something like ANUGA, you can basically just fiddle with your elevation data, maybe throw up a couple of buildings here, and then see what happens with your 100-year flood. And the difference was a metre or so over a major highway. So they were able to say, go back and fix that up, sort of thing, or give us a new design, a new development design. So it's, it'd be great. Maybe it doesn't have to be ANUGA, but it'd be great if these sort of facilities were easily available to all the councils or to people who are doing development. It can be extended to large domains. So this is a full catchment area simulation. This is looking down on top. Oh, this is just a cute one that we're sort of developing a relationship with the Penrith Olympic Whitewater Stadium. We've got the elevation data for the circuit there, and so we can run simulations. The Penrith Olympic Whitewater Stadium, I think, actually won the contract for the London Olympics. And of course they still sort of develop these sort of things by eye or by experience, but it would be fairly, well, we're trying to convince them it would be fairly sensible to have something like an ANUGA model to play around with these things. And here's a flow, that's the colours, just demonstrating the speeds. And you can sort of see the little hydraulic jumps here, hydraulic jumps one up there, along there. Oh, you can sort of see this thing if you look just down in a gutter or a river. They always have these interleaving sort of pattern of shocks or hydraulic jumps. So it's generating those things. And there's a hydraulic jump, a picture of it at the stadium, and a simulation of what we're getting there. So this thing comes down super critically and then it slows down here and makes a jump. Okay, so I can do all that. Boxing Day tsunami. Here's the time. Actually, I guess I better go quickly. Where's my thing? So here's a simulation of Patong Beach for the Boxing Day tsunami. At about 10 o'clock, the wave hits the shore and then pulls back, and then another one about, here we go again, which was bigger. The second one was bigger. And then that big pullback, and then another one. You can sort of see as it pulls up the shoreline, actually reflects off the beaches as well. Right, so the difficulty of something like this is multiple in the sense of getting the data for the elevation. So this was a combination. Out here you might have LiDAR data, which I don't think we had, but we just had ordinary survey sort of information. Out in the ocean you can get sort of nice, well, usually you don't need to be quite as refined, but you can get nice data. In between the wet and the dry is usually sort of the trickiest place, because it's too shallow to really use the ocean type techniques, and it's got water on it to use the land-based techniques. So in this one, I think we actually got a Thai Navy survey and digitised it. So the big time-consuming part of all this was actually getting the data ready. So that took months, literally. These simulations, in comparison, are just, well, say a day or something. So it's really integrating the data with the simulation, which at the end of the day will be the great sort of advance for these sorts of things. You stopped. Come on. Okay. Okay. Obviously you have to validate your code, and poor old Japan seems to be a good place to validate tsunami type problems. This one was back in the 90s, 1993, a little island off the west coast of Japan. So just this area is just down here is the island. And what happened, there was a particular valley where there was a 30-metre tsunami wave, whereas the base sort of wave was about 6 metres. So the question is, why would that happen? So it's around here. Actually, I guess it's there at this 30-metre wave. So the waves came down from up here, but as they get closer to shore, they actually line up and come into shore. Because this part here, closer to shore, goes slower. Get out, the ocean is faster, so it tends to turn around and go in that way. All right, so that particular valley, got a wave coming in here. Japanese are fantastic engineers, so they set up a flume with a model of the valley. So the ocean is here and flow up there. So this is not obviously the tsunami, but it's the results of a model of the tsunami. And you get a flow that'll come up now and then flow up that little valley. And so the real 30-metre tsunami was up that valley. And I guess even in this, well, obviously in this recent event in Japan, same sort of thing. Some places got away with 6-metre waves, some people got away with 30-metre waves. And that's usually the reason. There's some sort of topography that amplifies the problem. Here's a grid for this problem. We're have a fairly coarse grid out there. We're interested in here, so we have a very reasonably fine grid. This is actually a static grid. It's not sort of dynamic. We basically choose where we're interested in and then refine in those areas. So this is our simulation of that area, and it's going to, not quite sure, it's up one of these valleys that it's going to be amplified. So it's all about a confluence of different waves. So there's a wave comes in here, bounces off there. The wave that comes this way, bounces off there. You've got these two waves that have to sort of constructively sort of interfere. And then you've got this water up here, and it's got some momentum. And where's it going to go? Well, it's going to go up the valley and out to sea. And so it's going up the valley. It's going to just go as far as it can. It's got this momentum to go up the valley. So you can go around the coast and sort of identify places that are particularly at risk, and perhaps avoid building your house there. Oh, I guess I should show that one. This is a viewer that we have for that we give out with the ANUGA code, and in some sense that's been a nice sales point. It's qualitative, but you can sort of take it and show your boss, this is what the code can do. So that's helpful. So having and of course that's based on open source. So that's based on Open Scene Graph as its base. And
Can you download those model results as well?
Yeah. You can run these from our code.
That's interesting. If you look at that, you wouldn't think in that valley, you would think you'd be safe because the
lines
are actually quite high.
Yeah, exactly.
Quite high, so,
yeah. So you might want to run that way instead of up that way, if you know what I mean. Which, of course, you could build into your evacuation sort of routine. So instead of having your evacuation going up that valley, you'd have some stairs going this way to get out of the way. Okay, so just to prove that it's not just qualitative, you always have to sort of do some sort of quantitative comparison. So we've got 3 gauges here, and here's the experimental data for that one, and here's our model. Of course, it actually takes pretty hard to get a 200-metre long flume to be completely still. These are, once, whatever it is, some small percentage of the centimetres here. So it's still a bit of wonking going on there. Of course, we can start off with a 0 initial condition. But anyway, the waves come in, you get drawdown in this case to start with, then you get a wave hitting, then you get another wave. So these are these reflective waves that we saw actually in the qualitative movie. Obviously you can't get everything, there's more information in the experiment, but that's pretty good match up with the experiment. I think most people are very happy with that sort of result, and it happens on the other 2 gauges. Okay, so I've used up my time, but I've only got a couple more slides, so I'll keep going actually, if you don't mind. So what is it? Written in Python. Okay, so the history of that was that we were doing most of our coding. Well, initially our coding was in MATLAB. Then we did some data mining, and that was still in MATLAB. And then we got a parallel computer with 14 odd processors, and then MATLAB said, well, we want to change the license to times 14. And we said, well, bugger that. So we went, what could do the same sort of thing? What could basically be, and of course we weren't just worrying about the data mining, we were worrying about dealing with the textual data. So Python sort of came to the forefront. This was late 1990s. So we went Python, and then of course we had this project with the dam break and the storm surge. So we thought, oh, Python's good. Obviously, it actually helped us a lot. Coding in MATLAB, at least back then, it wasn't a computer science type language. So we had, classes and object-oriented ways of going. So that was very good. It had support for unit testing, which back then MATLAB didn't have. Or you could have done it yourself, of course, but it, had everything sort of set there in Python. So that was very good. Of course, you could write the bottlenecks in C, so that was good. It was open source, so we didn't have to pay for it. And when we gave it away, which was probably even more important, as an academic we don't have to pay that much, but whenever there was sort of anything semi-commercial, then there was real money for people who were getting our code. So that was good, the open source was good. We had software engineering people come in and help us, so we actually started using unit testing, which was fantastic. We put it onto Subversion at the time, and we set up a track site. So a combination of the open source, sort of licensing ideas, and I guess the open programming, agile programming sort of ideas also added to the whole thing. So, as I say, this has basically been going through about 2004. We probably should have more, but we've got 1,000 odd unit tests now, and we actually have refactored a couple of times. So this is probably the first time I've ever had a project that actually has kept going, the actual same sort of code has been going for more than a few years. And over the years, we've had a number of students, a number of people from GA. So 20, 30, 40, 50 people have worked on this at different stages. So it's still working. I guess I should just show you quickly this. So this is a script. It's 1 or 2 pages. Don't want to go into the details. But you set up your domain, you set up your quantities, the heights, the elevation stages, the water heights, set up some boundary conditions, and then you let it run. So this for loop is basically where all the calculations are done. And this actually is very good. We use yield, so it goes into some inner time loops and the code is calculated. But what a user, your civil engineer can do, is they can put in all sorts of things here to interrogate what's going on, and they can say, "Oh, maybe I'll change the height of the elevation. Maybe I'll remove something like a dam break." So they can actually sort of do that. So this idea of actually getting access sort of to the inner code, inner working is really good. Something you can do in other languages, but Python provided this facility up front. And that's, if you're ever doing evolution type problems, getting down into the loop is always the tricky thing. You want to maybe define a visitor or something. But it's all a bit too hard for someone who just wants to say, I want to change the height of the water or whatever. Whereas this way you can do it. So I think actually in some sense that was one of the main reasons why we liked Python for this project. That one thing, yield. And then you can just code up certain sorts of terrain to see the flow. And as I say, get beautiful sort of hydraulic jumps here, and reflections of boundaries, hydraulic jumps here, whatever. So I can do all those sorts of things. So why did we want it to have the open source? We had contracts with GA. We had the problem of IP. Open source seemed to solve that problem almost immediately, so there was no problems with IP. Basically, I guess we own, people who code it have the copyright. We sort of own the IP if we make the algorithms, or if the GA person makes an algorithm, they have the IP. and they can publish it and what have you. Obviously, as you say, someone asked, can we get hold of that? Yeah, it's publicly available, so that's great. We're getting people to reuse the codes and develop and build more sophisticated codes. Helps capacity building, both at GA, for instance, GA, I guess here at ANU, and out in the councils. I mean, we've still got a fairly small group of council members because obviously we don't have the resources of a two-flow or something like that, which might have 30 or 40 people working on this. But over time, we're sort of going definitely in the right direction. So my hope is that over time we'll build up a bigger and bigger group of people in local councils actually using this sort of code. And indeed, if people want to check our results, they can download it and actually just run the thing and see that it actually is producing what we're talking about. And we are moving forward. Storm surge is a little trickier than tsunami modelling because storm surge has all the things of tsunami modelling plus pressure of the cyclone changes the height of the water, the wind changes it, Coriolis effects changes it. So there's different sorts of frictional things to think about. So storm surge is actually is a trickier question, a little bit harder, lots more parameters to try and fit. We've got kinematic viscosity in there, so that means the thing is more sluggish. So maybe more like the stuff that we saw from the Japanese tsunami after it collected all the crap. We're always trying to improve the underlying algorithm, and indeed the wet-dry interface is our particular problem. We've got a set of 1D pipe flow code, 1D ANUGA, so to speak, and we're thinking of integrating those. If you've got a flood over a council area, a lot of the water goes down into the drainage system, so important we have that. And then, of course, you want it to run quickly. So we've got an MPI version of it. We want to improve that so we can run on multiple cores without too much trouble. But it does seem very tempting to develop a GPU implementation as well. So if anyone's interested in helping us implement a GPU or the multi-core, I'd be very happy if you'd come and have a chat. So I think that's my end. Sorry I was a bit late.
Sure. So the present from us, Steve.
Oh, that's very nice.
All right, thanks, Steve, for your talk.